and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today we're moving air. We're moving it through a tube to make a Stomp rocket, vacuuming it out, turning it into a vortex, and taking it with us underwater. All on this episode of Science Max, Experiments at Large. That was amazing! Greetings, Science Maximites. My name is Phil, and it's moving day today on Science Max, Experiments at Large. Let's see, where do I put this? This is probably a good spot. Today, we are moving air. You probably don't think that moving air will have a huge effect, but you'd be surprised what you can do by just moving air. But don't worry, we're not just gonna move the air around in boxes. We are going to build a rocket! And this rocket uses the science of stomping on something with your foot. This is a Stomp rocket, and it works by stomping on this plastic bottle, and air shoots through this tube and pushes the rocket up into the sky. And here is how you can build one of your very own. And remember, if I go too fast, don't worry. All of the steps are on the website, so you can follow along at your own speed. All you need is a 2-liter plastic bottle, 3 kinds of tape: electrical tape, duct tape, and science tape. Science tape is just the same as invisible tape, but I use this kind of tape for science. Then you want some plumber's tubing and some construction paper to make your actual rocket. First, you want to take your plumber's tubing and cut it into 3 lengths. And when I say you, I mean an adult, because you need to use a saw. So you saw it up into a long piece, a short piece, and an elbow piece. We want to make a long tube at the top, and then we also want to make a tube at the bottom so we can attach our 2-liter bottle to. And there we go. Ta-da! Ready to go. But of course, it doesn't stay up, so we have to attach it to a base. And it will look like this. And you see, it's been attached with duct tape here, and I've used electrical tape, and I've wrapped that part around there. Now, building the rocket. Wrap the paper around the tube and tape it with your science tape. Tape the top closed so no air escapes. Then cut a semicircle to make the nose cone, and 3 hoops for thrusters, and tape them to the bottom. There you go. The rocket fits on the tube just like that, and when you stomp on this bottle, it launches. But here's the most important part. The one most important rule of launching rockets. You shoot rockets outside. Come on. Once you get outside to a nice open area, and you bring your safety glasses with you, all you need to do to make the Stomp rocket work is, of course, stomp on it. You ready? Here we go. 3, 2, 1. Whoa! You see that? That was amazing. Okay, so this is where we're gonna start with the Stomp rocket. I'm gonna meet Chris from Logic's Academy, and he's gonna help me max it out. In fact, he's probably at Science Max headquarters already. I should get over there. Okay, where's the... Oh, there it is. Okay.
How you doing?
It's good to see you.
You too.
Chris is from Logic's Academy, and you guys do in-class robotics workshops, right?
That's right, we do.
Great. Well, I was hoping I could get your expertise to help me max out the Stomp rocket.
Yeah, Logix makes one of these. I totally think I can help you with that.
Fantastic. So it works great. I just want to make it bigger, better, more maxed out.
First off, we can start by making this pipe a little bit bigger. So a larger pipe, more airflow, bigger launch.
Okay, let's do it. Cool. Moving air isn't that hard, right? I mean, air is super light. How hard can it be to move? Well, here's an experiment you can do that lets you measure how hard it is to move air. So what I'm gonna do is I'm gonna hit the ruler with the broom. It's gonna go over there. I hit it, and it moved, no problem. So we're gonna do it again, except I'm gonna add just a couple pieces of newspaper. All right, ready? Aha, the ruler broke, because this time I wasn't just moving the ruler, I wasn't just moving the ruler and the newspaper, I had to move the ruler, the newspaper, and all of the air that was on top of the newspaper. And that resistance was enough to break the ruler. Pretty good experiment, right? Let's max it out. I've got more table space, I've got a piece of lumber, and instead of a newspaper, I have a tarp. Now the tarp is very light. It is not the weight of the tarp that is going to be the difference. It is how much air I need to move when I hit this piece of lumber. And I've got a Science Max hammer. So first of all, you're not gonna try this at home, right? Deal? Okay, deal. No trying this at home. Okay, here we go. Moving air, test 2.0. It broke, and it didn't even move. Did you see that? I wonder if we can max this out even more. 2x4, which is much bigger than the piece of wood we used last time, and a sledgehammer. Here we go, moving air experiment 3.0. Yeah, science. Whoa. So I've joined Chris from Logix Academy, and we are maxing out our Stomp rocket. To do that, we're gonna use
Larger pipe, more airflow, bigger launch.
The theory is that moving a larger volume of air through wider pipes will make our rocket work even better. So we get to work. This version is built exactly the same. We cut and attach the pipes, a long piece, an elbow, and a short piece, then secure them all down. We attach the plastic water bottle and tape it so it's airtight. And then the only thing to do is make a new rocket that fits over the larger pipe. Ready to try it?
I'm ready to try it.
All right, let's do it.
Let's go.
1, 2, 3, go! That was amazing! In the end, though it worked, it wasn't much better than the smaller rocket. I think we could still do better, right?
Oh, yeah.
This is Science Max, not Science Medium. Right, okay, let's go back to Science Max headquarters. Vacuum sealing. That's what you call it when you take all of the air out of something, often a bag, to seal in the freshness of food. I will demonstrate using this Science Max banana. 100% banana, but with added science.
Not all bananas contain science.
Here's how you can do it at home. Put your food in a bag, seal it most of the way, because we have to take out the air from the bag. And we will do that with a straw. Put a straw inside the bag, and then suck the air out of the bag, and then seal it at the very last second. There, a vacuum sealed banana. Now I know it's kind of hard to see that it's been vacuum sealed because bananas don't really crush much when you take the air out. So I like to use stuff that has a lot of air in it to begin with. In fact, there are special bags that are specifically for vacuum sealing that are supposed to store big and bulky items that have a lot of air in them, like this pillow. See this nozzle right here? It's designed to be used with a vacuum. So, what you do is you put the vacuum on this nozzle, open it up, and then you turn the vacuum on. Oh. The vacuum is sucking all the air out of the bag, just like we did with the banana. But because the pillow is full of air as well, it starts to shrink and shrink. Then you pull off the vacuum and you tie the seal off, and all right. And ta-da! A vacuum-sealed pillow. Okay, let's max it out. What could possibly be more maxed out than a vacuum-sealed pillow? Vacuum-sealed fill. Okay, I put plastic bags against the door and then sealed the edges with duct tape. And of course, I didn't put any plastic over my head because you never put your head in a plastic bag, right? Well, let's see if vacuum-sealed fill, it works. Whoa. Hey, it's working! Haha! The vacuum sucks all the air from the bag, which seals the bag and me in it to the wall. That means I should be able to knock this milk crate out from under me.
Air pressure, or the lack of air pressure, is keeping me sealed to the door.
I'm completely suspended! Uh-oh. I shouldn't have done that. No.
So our larger version of the Stomp rocket worked, but it didn't go as high as the first version. Chris and I see how we can improve the design.
The larger pipe and the larger rocket works really well.
It does work really well. I am afraid, though, that the larger pipe means that the same amount of air is flowing slower out the nozzle than it did before.
Oh, so because we're moving only this much air, it's not going to go as fast because this is a bigger tube.
We need a bigger volume over here to match our larger
So a
nozzle.
bigger bottle.
That's right.
I got a bigger bottle right here. Ha-ha! Bigger bottle! So hold that, and then all we have to do is tape the bigger bottle
I'm not sure
on.
if that's gonna...
Yeah, like this.
Still, though, I'm afraid...
Yeah, so then all I need to do is tape it on.
Chris and I attach a larger bottle to our tube. We just need some risers to adjust the height, then we tape it on and we're good to go. Everything else, including the rocket, stays the same.
I still don't understand how you're gonna step on this one. It's just too stiff.
I have a plan. Ha 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 ha! Sledgehammer! You ready?
Yeah, I'm ready.
Okay. 1, 2, 3! It blew the top off the rocket.
Right off
It
the
also
top.
blew the bottom.
Looks like it's a bit rigid to change its volume so quickly.
So it's kind of a one-time use thing, huh?
I think so.
So why don't we try increasing the volume? Even bigger tube,
Yeah.
even bigger container.
What's bigger than that? That's the biggest bottle they make.
What else holds air?
What about an air mattress?
Do you think we could use an air mattress?
I think we could, yeah, a really big air mattress.
Oh, totally. High five. I love that idea. Moving air is a lot of fun, especially if you use one of these, a Vortex cannon. They're pretty impressive and they use some pretty amazing science. I'll show you how to build one. It's pretty simple. All you need is a plastic cup, you want a balloon, something round, an elastic, scissors or a craft knife, and a pen. Here's what you do. Take your balloon and cut it just where it gets wide. You take the mouth of the cup right there, and you have to stretch the balloon over the top. And then you want to put an elastic around it, keep it in place. And this now is a surface on the top, and that's what you're going to use to pull back and create your burst of air. But of course the air's not going to go anywhere until you make a hole in the bottom. So here's what you do. You take your round thing and draw a circle, and take your craft knife or a scissors and an adult and get them to help you cut out a hole. And when you pull back on the balloon, a burst of air comes through the hole. But the air has an interesting shape. Now I know what you're thinking. You're thinking, Phil, air is invisible. You can't tell what shape it is. Well, I can show you. Come on. This is my maxed out Vortex cannon. It's made out of a garbage can. I've got a hole in here, and this is a shower curtain with a ball that I can get a grip on and pull. And then it shoots forward like this. Now it makes a big puff of air, but again, the air is invisible, so we don't know what shape it is, but I can help with that because I've got this, a fog machine. I fill the inside of the garbage can so we can see what the air is doing when I fire the Vortex cannon. Okay, come on over here. Ready? Whoa! Okay, ready? Check it out.
The Vortex cannon shapes the air into a ring, called a vortex.
It makes a ring. Well, actually sort of a donut.
Because of its shape, the air in a vortex can move much farther than air that doesn't have a shape.
Vortex cannon. Air that has a shape goes a lot further than air that doesn't have a shape. And it's also way more fun. Woohoo! Little to the left, Ramona. Okay, now that's too far left. I don't know what you think. Oh, hey, I don't suppose you're going on vacation anytime soon. Well, if you haven't, this decided where, may I suggest underwater. But don't forget to pack the most important thing when you go. Hat? Nah. Ukulele? Nah, forget about it. Oh, chicken? No. Sunscreen? Forget about it. Teddy? No, if you're going underwater, the most important thing you gotta pack is air. You see, human beings have been coming up with ways to go underwater for a long time, but the thing is, you gotta bring air with you because, you know, breathing is good. Check this out. It's a diving bell. One of the first ways humans used to be able to take air with them when they went underwater. You see, it's a big, heavy bell, and it's lowered from a ship above on a rope. And when it gets lowered into the water, it traps a bubble of air underneath. So you can swim around underwater, but then when you need to breathe again, you don't have to go all the way back up. You just pop under the bell and take another breath. Bells like this were actually much bigger when they used to use them for diving to hold more air. Huh? Ring-a-ding-ding. What do you think? You want this? No? It's okay. I got something else. Hold on. Check this out. It's an old-timey diving suit. Air is pumped in through these hoses here, which means the diver has a constant supply of air, which means he can stay underwater longer. What do you think? Yeah, no? Okay, hold on. I got something else. Yeah. This is it. The ultimate in bringing air with you. The scuba suit. This tank holds compressed air, which means it can carry a lot of air with you, which means you can stay underwater for longer. So I'll tell you what, I'll wrap up all three things. What do you say? Yeah? You'll take them? Okay, great. Let me just wrap them up for you. Come on, Teddy, let's go find the bag.
So our large Stomp rocket hasn't worked perfectly. A small bottle didn't move enough air, but our larger bottle was too rigid to stomp. And when I used a sledgehammer, it was so sudden the bottle broke and also blew apart the rocket. Chris and I need a large container of air that is soft enough to change its shape easily. So here's the current plan. An even larger pipe, an even larger rocket, and we use an air mattress. We make 2 holes in the air mattress, one to fill it up with a leaf blower, and the other hole to go out the tube to the rocket. Since an air mattress holds lots of air and is very easy to change the shape by jumping on it, we figure it'll be a great way to get lots of air through the tube to launch our rocket.
Okay, let's do it.
Let's do it.
All right, we're gonna go 1, 2, 3, jump, right?
Okay, yeah.
1, 2, 3.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello! Welcome to Cooking with Science. I'm Buster Beaker. Whenever friends come over, I like to make my famous potato chip recipe. And look at this bag of potato chips. Quite large, there must be a lot of potato chips in here, right? Well, let's open it. What? This potato chip bag is mostly air. Why do potato chip bags have so much air? Well, to tell you the answer to that, I have to tell you the story of 2 bags of potato chips. Here they are. This one full of air, and this bag of potato chips, there's not much air in it at all. Why don't they make them like this? Well, let's find out. First thing that happens is the potato chip bags come off the conveyor belt at the potato chip factory where they get packed into a crate. Here's a crate here. So let's really stuff them in. And then the crate gets boxed up and shipped off to the store. Oh, it's a bumpy ride to the store today. Now we're at the store, and then you come along. Bags of potato chips. What else should I buy today? Oh, I know. How about a cantaloupe? Very nice. Some apples, yes? And take it home, walk along, and you get to the kitchen, you have a choice. This bag of potato chips, where all the potato chips are light and fluffy, or this bag of potato chips, which is not exciting at all. And that's why potato chip bags have so much air, to protect the potato chips from getting crushed. speaking of potato chips, time to get back to my recipe. What is it? It's potato chip soup. Well, I'm Buster Beaker, and thanks for joining me on Cooking with Science. Perhaps a little bit more cooking.
Okay, so where were we? Oh, right, our maxed out rocket. A much larger pipe, a large air mattress, and the largest rocket yet. Let's see how it goes. 1, 2, 3, jump. 1, 2, 3. Whoa! Yeah! There he goes. All right, let's do it again.
Okay.
1, 2, 3. It works amazingly well. The large volume of air Chris and I can move by both jumping on the air mattress gets transferred through the large pipe, and even though it's a giant rocket, it sails higher than any other version.
That was great.
That was amazing. All right. There you go. Science Max, experiments at large, moving a lot of air.
That has to be the biggest Stomp rocket ever.
Biggest Stomp rocket ever. Let's do it again.
Okay.
Okay.
Oh, it smells so horrible.
It's a diving bell. And that didn't work at all.
That's acting, my friends. Oh, friends, that is so bad.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode of Science Max is all about building things strong. 2,
And let's do 3.
an arched bridge, giant house of cards, magical stacking books, and more.
Oh, I thought they were gonna do it.
All on this episode of Science Max, experiments at large.
Oh, hello, Science Maximites. We've got a lot of work today, so I was just getting prepared. You know, taking something flimsy and making it strong, that's what scientists and engineers do every day. And it's also pretty fun. You take something that's not that strong, and by the way you build it or put it together or change its shape, it suddenly becomes a lot stronger than you think it was. So I thought that's what we should do today on Science Max Experiments at Large. We should build something. So we're gonna build an arched bridge, and we're gonna build it out of sugar cubes. So here's what you need. You need some sugar cubes, you need some sandpaper, and you need some modeling clay. So first, you want to make some abutments out of your modeling clay. What is an abutment, you ask? It is this. They distribute the force laterally from one side or the other. I like to use this. This is half a roll of duct tape, and so it fits in just like that, and you see, it's a perfect arch. If you just take sugar cubes and you try to stack them into an arch, it's not going to work because the sugar cubes may not even fit all together, and you can see only the bottoms are touching. I take out the guide and it all falls apart. So here's what you do. You take your sandpaper and you change the squares into trapezoids, and you start sanding down your sugar cubes into trapezoids. Basically, you want one small side and one long side. Thin at the top, wide at the bottom, or wide at the top, thin at the bottom. It's a trapezoid no matter which way you hold it. Put it on the bridge and see. And as you go, you will see if you're doing it right, there will be no gaps. If you go to the Science Max website, there will be a guide that you can use to help you make the sugar cube bridge, so you don't have to spend as long as I did making this one. And then the most important part is the keystone. That's the one that fits in right at the top, just like that. And when it does, you can take away the guide and it stays up. Isn't that cool? It stays up without any glue, without any mortar, all based on the shape of these sugar cubes. The cool thing is, it'll hold the weight of a whole car, provided you have a very, very small car. The reason why it works is because the weight is distributed along the arch into the abutments and down into the ground. That's what makes an arch bridge so strong. And that's what we're gonna do today. We're gonna max out an arch bridge. So I think I'm gonna need some help though. Maybe Sonia from the Ontario Science Center. She really knows her stuff. Yeah, I'll go there and I'll see if she's busy. All right, come on, let's go. Hey, Sonia.
Hey, Phil, how's it going?
It's going good. I was wondering if you could give me a hand with something.
Okay, what's up?
I'm building, well, it's easier if I show you.
All right.
Do you mind coming back to Science Max headquarters? We can take the portal.
But that thing doesn't always work.
Oh, it is fine. Well, I mean, that worked just fine. Uh-oh, it usually makes a beeping when I do, oh, it's out of batteries. Oh, I told myself, Phil, charge the remote before you leave the lab, and then I...
Where have you been? Breathe.
The remote ran out of batteries, so I had to run the last 3 kilometers.
It's all right.
Because
You made it.
Long story. So the Sugar Cube Bridge, you had a chance to look at it, right?
Uh-huh.
This works on any scale, right? It should, no matter what size arch, it should be the same, right?
Definitely.
Good, because what I want to do is use these abutments, but go to these abutments.
Oh.
So we're gonna start the bridge here, and I've already created a thing that we can use to put
Support?
the sugar cubes on as we go up, so that we can make sure that it becomes a
Phil.
perfect arch. Yeah.
Do we have enough sugar for this?
Yep. I got tons of sugar.
Wow.
Yeah. So I think we're gonna need some glue because it's gonna be really hard to get these to stay
Yep.
right
on.
there without a little bit of glue. We're gonna make a giant arch, maybe some walls, and we'll see what happens.
Let's do it.
Oops. An egg. Now you might think of eggs as kind of flimsy, and they do break pretty easily, but eggs are actually stronger than you think. It's because they're, well, egg-shaped. You see, the top of the egg is like a little bit of an arch, and the bottom of the egg is also like an arch. And arches distribute the weight, just like they do in a bridge. Here's how you can experiment with how strong eggs are. First, you want to get a pair of gloves to protect your hands from the shell, just in case anything goes wrong. You should also tell an adult that you're doing this experiment because if it does go wrong, you're gonna have some mess to explain. And also, you should probably put on some safety glasses. Now, here's what you do. Take your egg and carefully put it in your palm just like that. And put it against your other palm, and you're gonna push in directly on either side of the egg. Start pushing harder and harder. You can even lace your fingers and press even harder. And if you do it right, the egg won't break. Pretty amazing, right? So, just how much weight does an egg hold? Can one egg support my entire weight? Let's find out. I'm gonna lift my weight up like this and lower myself down. And no, cannot hold my weight. Can my weight be supported by 2 eggs? Oh, nope. Phil's weight, 4 eggs. Oh, I thought they were gonna do it. Nope. My weight on 8 eggs. Huh? My weight can be supported by just 8 eggs. Science! Whoa, careful.
Sonia and I are on a quest to make a maxed out sugar cube bridge. The reason why an arch works is because the weight, or the load, of whatever's on top of the bridge is carried outward along the curve of the arch to the abutments at each end, which carry the load and keep the ends of the bridge from spreading out. No matter what you build your bridge out of, sugar or stone, the science stays the same. Sonia and I are building a much larger bridge out of sugar cubes. We're using glue to help the sugar cubes stay together, just like stone bridges use mortar. And when we're finished, it was pretty impressive.
A massive sugar cube bridge, right? High fives for that.
The moment of truth comes when we take out the support and...
Yeah! It works! Okay. Giant sugar cube bridge. So do you think it'll hold some weight?
I think it definitely should, because right now we have an arch, perfect arch, and the weight is being distributed to the sides, the base.
So that's what it's for, right? We can put weight on there?
We can definitely put some weight.
One to start?
Let's start off with one.
Okay.
And let's see how it goes.
All right.
Here we go. All right.
Yeah, one book, yeah! All right, sugar cube bridge,
1 book.
2 books.
Are you nervous?
Yeah! Sugar cube bridge, 3 books.
3 books.
Oh, that was great. It held up 3 books.
3.
Well, technically it held up 2 books and broke on the third.
So it's kind of still far from how much weight we want to hold because we want to cross it.
We definitely want to cross it, so that means we need something bigger and stronger. The cube works.
You're right, because the cubes are great because that keeps the science the same.
Yep.
Right? So something cubular. The milk crate, really?
Definitely. I think we should use those. It's a cube.
It is a cube. A whole bunch of milk crates, and we'll see what we can do.
I think that sounds great.
Awesome. Whoa. This is a Prince Rupert's drop.
It's a piece of glass that has a long snaky tail and a bulb at one end.
So what's so interesting about a glass tadpole? Well, I'll show you. And remember, this is just glass. Oh, Prince Rupert's drops are very strong, almost as strong as steel. It's all in how they're made. Molten glass is dropped into cold water.
What happens is the outer part of the drop cools off first, leaving the inner part still hot. When the inner part eventually cools, it contracts, pulling everything in tighter and tighter, keeping it under a lot of tension. And because it's round, the force you put on it is distributed all the way around, just like the force is distributed on an arched bridge.
Until you get to the tail. Just the tiniest break in the tail, and
It explodes. All that energy is released in a chain reaction. Why it's so strong you can hammer on one end, but explodes when you break the other, puzzled scientists for centuries.
but now we know it's all in how it's made.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Send in the next applicant.
Okay, don't let them see you. Don't let them see you. Okay, magic smoke. And here we go. Big entrance.
Behold, it is I, Overwhelmo. You again. I only have to demonstrate magic one time, and you have to let me into the Wizard Academy. And last time does not count. So prepare for your mind to be boggled and your eyes to also be boggled, because I shall do a trick. I will just get to it. Here is a book, behold! And now, feast your stupefaction as I produce another book, ha-ha! And then, 2 or 3 more times, behold, that's good. Behold! And now, look upon the wonderment as I stack these books on top of each other, like this. And now, feast more stupefaction as I cleverly move the books off the table. And now comes the magic word. Now, I say the magic word. The magic word
And behold, the book is levitating. It is completely off the table. I have done it. Magic.
No.
No?
Not magic, that's science.
But the book is levitating.
No.
Look, it's not even touching the table.
No, it's being supported by the books below because of the center of mass.
Preposterous.
I'm afraid it's very preposterous. Each book is balanced on the one below in a way that the center of mass is behind the edge of the book below. And the entire stack's center of mass is behind the edge of the table. So it may look like magic, but it's science.
So, I can't get into the Wizard Academy?
No, I'm afraid not.
Aye, good. Alakazam, you will rule the day that Overwhelmo did not. I will return, and then you will see. Oh, ow.
Sonia and I made a large bridge out of sugar cubes, and it didn't hold much weight. So now we're going to try making another arch bridge, but instead of sugar cubes, we're going to use milk crates.
There we go. I've made some abutments out of giant crates, and this is where we're gonna start our bridge, and they start there, and it goes in a big arch, but we're gonna be using
I brought milk crates.
milk crates. High fives, high fives.
So we start our bridge,
This is a straight line, it's not an arch.
It's not an arch.
but it's clear we have a problem.
Okay, ready?
That didn't work, Phil.
It's like we're back to the beginning again. So this is like two straight
We
lines.
have two straight lines,
It's
yep.
like a triangle.
We need an arch, so we're gonna need a support.
Sonia and I build a support to help us make a curve the milk crates can follow. But after we finish stacking, there's a problem.
It doesn't look very solid.
Yeah, it doesn't, does it?
Here.
Oh, yeah. Because there's a gap at the top of all of them. Look, that one, there's a gap. There's a gap there.
There's a
There's
big
a
one
gap
here.
there.
It's
Well, I
not
mean,
making our bridge very solid.
There's only one way to find out for sure,
You can try it.
is to pull this out and see if it stands up.
Let's do it.
Okay. So, didn't stay up.
Didn't stay up.
Okay.
That's all right, though.
I'm not sure why it isn't staying up. Like, the sugar cubes were cubes.
That's a cube,
Milk crates are cubes.
but we did change the shape of the cube.
Oh, yeah! If you remember, when I first built my sugar cube bridge, it didn't work with cubes. You have to sand the cubes down to make them into trapezoids. You can't build a perfect arch out of cubes.
So they were wider here and then narrower there so that they had... Oh, so that's the problem.
Yep.
So I could, like, cut it? I could cut it. I could cut it.
You could.
I could
That's
cut
gonna
it.
take a long time, though.
If we cut the milk crates into trapezoids, everything will work, right? Right? We take a milk crate and with the right safety gear, we cut it so we can reshape it into a trapezoid.
Good.
And it works. But
It's gonna take a long time, isn't it?
Definitely. So how about this? I have an idea. So remember when we did the experiments and we had lots of V gaps?
Yeah?
How about we put some wooden wedges into those gaps to make it one secure structure?
So it was sitting like this.
Exactly. So what we're gonna do is insert wooden pieces right here, so we'll fill those gaps.
I get
and
it.
we'll make it one secure structure.
Instead of cutting all of our milk crates, we can keep the milk crates.
Yep.
And they can be solid and we just add to it rather than take away.
Taken away, exactly.
That is a smart idea. Okay,
So-
let's make some wedges.
All right.
Oh, hey, how you doing? Let me guess, you want to build a strong structure, something that'll stand the test of time. Well, you know you gotta use the right kind of shapes. Look at this, a square. Now, squares have gotta be strong, right? Well, maybe. Maybe if you press straight down on it, but watch as I push to the side. Oh no! The thing that I have built is now collapsing because squares aren't in fact strong after all. If only I had listened to Sal's sage advice. Yeah, squares aren't gonna cut it. Fortunately, there's a shape that's strong in all kinds of ways. A triangle. Okay, so you heard of triangles before, good for you. But look at this. You can push down from the top and it doesn't move, or you can push from the side and it doesn't move. Triangles are awfully pointy. How do I build with them? Observe! Ha-ha! Triangle here, triangle there, platform on top. And watch. No matter how I try to shift it, it stays solid. And check this out. Triangle here, second triangle there, and a third triangle shape here. That's like 3 triangles for the price of 2, huh? That's a good deal. So there you have it. The triangle, one of the greatest shapes to build with.
This is a house of cards, and if you've never built a house of cards, you should definitely try. Try, because it's not easy. What you need to do is you need to make triangles with the cards. If you do it just right, they'll stay up. Then you take another pair of cards, like that. You take another card, and you put it on top. And it stays up.
Keep on building by making triangles and putting another card across the top like a roof.
Then, when you're ready, you can start to make a second layer.
It takes a lot of patience to make a house of cards. But with enough patience and really steady hands, you might be able to finish it.
There we go. A house of cards. Now, let's max it out. Shh, backing away slowly. Backing away slowly.
To build our maxed out card house, the Science Max build team and I used large pieces of foam insulation, which were super light and easy to work with. Once we set up the first layer, we needed to bring in a scissor lift so we could keep building the next layers. By the time we got to the top, our card house was 10 meters tall.
Yeah! Giant house of cards! And now that I've built a giant house of cards, what do I do with it? I knock it down. Science! I'm gonna build it again.
Sonia and I are rebuilding our milk crate bridge. Since cubes don't work if you're trying to make an arch, and changing the shape of each milk crate would take too long, we're using wooden wedges to fill the gaps at the top of the milk crates. Once we get the wedges in, the milk crates have support at their tops, and they make a perfect arch.
Are you ready?
I'm ready.
All we have to do is pull the wooden thing out, and if it holds up on its own, we've done it.
We pull out the support, and
It stands!
it works! The bridge supports itself! Now it's time for the final test.
We try to walk on this bridge.
So we spent some time making sure our bridge was safe. We added a crash mat, and
We built a second arch
We sure did.
so that it's a little bit wider, and it feels very solid. So the only thing to do now is to test it.
Test it out.
You gonna do it?
I absolutely will.
All right.
Sonia puts on a helmet and gives it a try. And sure enough, it works!
Yeah! Milk crate bridge!
Milk crate bridge!
Milk crate bridge! Milk crate bridge! Milk crate bridge! Woo-hoo-hoo-hoo-hoo! Science Max experiments at large. Milk crate bridge!
Yay for science!
High five! High five! There, not going great so far.
Behold!
Beginning steps. I see a problem. Look, I can spin it on my finger. Ow!
I was wondering if I could ask you a question.
Yeah, go ahead.
What? Do your hair like that?
Well, you don't like my hair?
Well, it's okay, but you know, what if you parted it to the other side?
Huh.
Never thought about that. Maybe I should try that.
Well, I'll say, Henry, that bridge is sure sugary.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large.
Science Max!
This episode of Science Max Experiments at Large is all about light. And bending light to your will.
Huh? Right?
And challenges me to an ever more tricky game of light manipulation. Plus lasers, periscopes, and what does that have to do with light?
Cut to animation!
Find out on Science Max Experiments at Large.
Greetings, Science Maximites. I'm Phil, and today on Science Max Experiments at Large, we're going to be looking at light. Okay. Just stay. That wasn't supposed to happen. I was supposed to press that button, and there was supposed to be all these lasers and special effects, but it didn't. Well, today on Science Max Experiments at Large, we're not going to be doing one experiment. We're going to be doing a number of small experiments because we are going to do a light manipulation challenge. I'm going to get an expert, and she's going to challenge me to a game of light manipulation because I am the master of light. Oh. Well, at least the green lights are working. And okay, forget it. I'm just gonna turn it back to normal. Come on, back to. I'm gonna work on that later. I'm gonna need an expert to help me though. Oh, I know. Anne would be really good at this. It really does look kind of weird in here, doesn't it? Oh well.
You okay?
Hi.
Hi,
Anne.
Phil.
Yeah, I couldn't see what I was doing. Here's your lab coat.
Oh.
Thank you for coming.
Great.
Now, you're from Let's Talk Science, right?
Yes, that's right.
All about science education, just like us. Now, you're going to challenge me to a light manipulation game?
A light manipulation game. I've been working on a series of challenges since last time we talked. Each
Awesome.
A little more difficult than the last.
Well, this is going to be great, because I am the light manipulation master.
Okay, well, we'll see about that.
Okay. Challenge number 1.
Take a seat.
Oh, that's easy enough.
I have written something on the back side of this ball.
Okay.
And I'm going to challenge you to read it.
Okay, well, I'm ready. I might be able to read it from here. Let's see.
All right.
Okay, I see something's written on it, but I can't read what it says.
What if you squint?
It looks like a couple lines, maybe? I can't quite tell.
Any ideas how to solve this challenge, Phil?
And I have to be in this chair?
Well, you can get out of the chair to set up your solution. But
Okay.
when you read what I've written on the ball, you have to be sitting in the chair.
Well, it's light manipulation, right?
Mm-hmm.
So, wait a minute, I've got flashlights in case the power goes out, so maybe I can use a flashlight. Haha, okay, ready? Pew! Doesn't seem to make it any easier to read. Yeah, I got nothing.
Do you give up already?
No, of course I don't give up.
I told you these were going to be challenging.
This is nothing. I will figure this out. I don't know yet.
You're going to have to get creative.
I don't know yet, but I will think of something.
Okay.
Okay, I will be back. Here, hold the flashlight. Not looking, not looking. I'm gonna go this way.
I'm going to wait right here.
Okay. Have you ever wondered why you end up upside down when you look at yourself in a spoon? It's because of light reflection. Light is made of photons. Let's say that these tennis balls bouncing off this wall are photons of light. Now, when the surface is flat, like a mirror, the photons, they bounce in and straight back out again. But when the surface is curved, the photons don't go straight out, they get reflected. So now, this photon is going over there, and if we had photons on this side, they would I don't even know where those ones are coming from. Then, okay, so we got photons on this side that are going that way, and photons on that side that are going this way. So the top becomes the bottom, and the bottom becomes the top, and that's why you look upside down when you look at yourself in a spoon. Okay, cut to animation, cut to animation!
A lens works by changing the direction of light, too. Lenses are made out of curved pieces of glass. When the photons of light pass through the glass, the curved surface makes their paths change. What was only this big before becomes this big when you see it. Lenses are used in microscopes to see things that are really small, or in telescopes to see things that are very far away. Both times they are making something small appear large. Anne has challenged me to figure out how to see a small object far away, and using a lens is my solution.
Check it out. It's a giant magnifying lens, and I'm gonna use it to magnify the ball so that I can see it.
Sounds great.
All right.
I set the lens in front of the ball, which end is turned so I can't see what's on it. I add a light.
Shine it on the ball so that it's a little bit better illuminated.
And then sit in the chair and ask Anne to move it so it's aligned.
All right, so bring it to your left. Yeah, keep going, keep going. Keep going, right about there. Try bringing it closer to the ball. Okay, wait, that makes it smaller. Try bring the lens away from the ball. Ooh, wait. Try a little bit further. Ooh, ho, ho, ho.
You're ready for me to spin the ball around?
Yep.
Okay.
It says 71.
Nicely done.
Easy. Solved.
Wait.
What?
That was just the warm-up.
Oh, yeah?
Yep. You ready for challenge number 2?
Challenge number 2!
I've got another ball.
Okay.
With something else written on it.
Wait. Are you coming back?
Nope.
Huh. But I can't even see you from here. Like how am I? Huh.
You're gonna have to manipulate the light.
I have to see around a corner? I have to see around a corner. All right. I'll think of something. So you remember the tennis balls in the wall, right? Right? Okay, so the tennis balls are photons, what light is made out of, and the wall is a mirror. Now, right now, the photons are hitting the mirror and bouncing directly back. But what happens if they come in at an angle? Like this. Aha! Those photons are reflecting off the mirror and going that way, which means if I want to see what's emitting those photons, I can see it from here. The same thing happens when you look in a mirror. Oh, okay, mirror. Whoa. The mirror reflects the photons over here. I can see the tennis ball launcher in the mirror, which means if there was a barrier, between me and the tennis ball launcher, I can still use a mirror, and the photons would reflect off the mirror and it comes straight to me, which is how you can use a mirror to see around a corner. In fact, periscopes work the same way. Let's make a periscope right now. Hey, it's dark in here. Oh, right, because I'm gonna show you my laser. So the light from my laser bounces off this mirror in a straight line. Haha, reflection. We can use the power of reflection to make the light go where we want it to. We're gonna build a periscope.
Submarines use periscopes because it's hard to see when you're underwater. A submarine will extend a periscope up above the water. The image up here gets transmitted down here. So someone looking through the periscope underwater can see what's going on up on the surface.
And here's what you need to build it. 2 cartons of milk, 2 small hand mirrors, scissors or a craft knife, a pencil, and science tape, which is the same as regular tape, except you use it for science. And remember, if I go too fast, you can always find these instructions on our website. Step 1, cut the tops off your milk cartons.
Take your mirror and trace out a rectangle as wide as the mirror, then cut it out. Put some science tape on your mirror and stick it in the carton at an angle. Then put a piece of tape on the inside. Then
Get the other milk carton and do the same thing. Put a mirror on the inside and then stack the milk cartons together. But don't stack them with the holes on the same side. Make sure you stack them with the holes on opposite sides. And here is what's going on inside. You've got your 2 mirrors, and one is angled like that, and the other one is angled like this. Light from what you're looking at comes in, hits that first mirror, goes down to that second mirror, and goes to your eye. You can use it to spy on people from below the table. Or from around corners. So there you go. Your very own periscope using light reflection. Did you know that your TV remote can be a flashlight? It's true. If you have the kind of TV remote with a little bulb on the end of it, then when you press the buttons, the bulb lights up. Yeah, I know what you're thinking. You're thinking, Phil, wait a minute, the bulb did not light up, and I've never seen the bulb on my TV remote light up when I press the buttons. Well, that's because your TV remote works on infrared, which is a kind of light you can't see, but you might be able to see it with a camera. If you have a digital camera or a camera on your phone, now you can see, It lights up. And because infrared light works the same way as visible light in that it will bounce off a mirror, here's an experiment you can do at home. Bounce the light off your TV remote off a mirror and turn on and off your television. Check this out. You get a mirror, set it up just right, and then aim the remote at the mirror and it turns off the television. Pretty cool, right? But now, let's max it out. I've got a complex series of mirrors set up here, and I'm gonna bounce the light from the remote all over the room. And here's what that pattern looks like.
The light from the remote hits this mirror, which reflects to this mirror, which reflects to this mirror, and then this mirror, and then this mirror, and then finally to the television.
Isn't that cool? There you go. Maxed out remote light bouncing infrared flashlight. I gotta come up with a better name, but still, it's pretty cool. Oh, right. Turn off the television and leave the room.
I solved Anne's first light challenge, seeing something far away, with a lens.
It says 71!
But now she's moved the ball around a corner, and now I have the solution.
Mirror! A mirror will let me see around the corner.
Clever.
Right? Okay, so all I gotta do is put the mirror in a position sort of like that, I guess, and then I'm gonna sit in the chair. If you could help me adjust that mirror. Keep going that way. Keep going, keep going. Yeah, stop. Nice, okay, go ahead and flip the ball around and I will read the message. It is too small. I can't, okay, I've solved this problem though. Okay, flip it around. The lens, I need the lens. So we'll use a mirror and the lens to, good. Yeah, okay. I'm gonna sit in the chair. Mirror in the chair. It is backwards. Oh yeah, a mirror inverts the image, doesn't it? Mm-hmm. That's okay, I can solve this. All I need, whoa! Other mirror is all I need to solve this problem. So if I take this mirror and I put it here, let's see, there it is. It says 42.
Nicely done.
I
Nicely
am
done.
ready for anything. What do you got planned for the hardest challenge?
Are you sure you're ready for this?
Totally.
Challenge number 3.
Challenge number 3 starts now.
What? Wait. No. This is a light challenge. How am I supposed to do a light challenge if it's dark?
You have to get creative.
But it's dark. Well, okay, no problem. I will think of something. I will be back.
Okay.
Okay, careful.
I'll be waiting. Careful.
So you already know about reflection, right? That's when the beam of light, say from my laser, reflects off this mirror and bounces in a straight line. But check this out. If I don't use the mirror and I shine the laser against the underside of the water, it also reflects, just like a mirror. This is called internal reflection. If I have a stream of water and I put my laser beam into the stream, you can see that the laser bounces around inside the stream of water. It's being internally reflected, and the laser isn't going straight anymore. It's following the stream of water down where the water goes. Internal reflection. Now I know what you're thinking. You're thinking, Phil, how does this affect me in my everyday life? Internal reflection. Who cares? Well, I can tell you why you should care in 2 words. Fiber optic. Wires. 3 words, fiber optic wires. You see, fiber optics carry information all over the planet. The internet, maybe even your television, travels through fiber optic wires. The good thing is, because of internal reflection, you can bend fiber optic wires any which way or around corners, and the beams of light continue to go straight down inside the wires and get out the other end, making it go where you want it to go. Internal reflection, science.
Back to our light challenge. I've seen something small from far away, seen around corners, but now Anne has turned off the lights. But I have a solution.
Ann? Ann?
Careful.
Okay. Sorry, I forgot how dark it was in here. Okay, I figured it out.
Okay.
I have a flashlight.
No.
So all I need to do...
No. Hold on.
What?
There's one more rule I didn't tell you.
What's the rule?
You can't use visible light.
How in the world am I gonna do this if I can't use visible light?
It's a challenge.
Wait a minute. Okay, here, hold my flashlight for a second. I'm gonna make a phone call.
Okay.
I think I know what to do. I'll be back.
Okay.
I'll be back.
Oh, careful. Oh.
Oh, hey, good to see you. Speaking of seeing things, let's talk about the rainbow. All the colors of the spectrum organized in a beautiful pattern. But what are the different colors? I mean, what makes them different? Well, it all has to do with the electromagnetic spectrum. This is visible light. All the colors of the rainbow. And take a look at that little black line that goes up and down there. That's the frequency of the light. Light is a wave. You see the wavelength is a little wider out here on the red side, and it's a little closer together here on the violet side? That's because every color of light has a different length of wave or wavelength. And that is what makes them different when we look at them. But if you think that's all there is to the electromagnetic spectrum, then you're mistaken. So what happens over here on the red side? Does it keep going? Yeah, it does. What? Look, we got infrared here, and then we got microwaves. These are the same kind of waves you use in your oven. And then we got radio waves, which are the same kind of waves you use in your radio. They're all part of the same thing as visible light, huh? Let's take a look at the other end. Remember these short wavelengths over here beside violet? Well, does that keep going? Yeah, if they keep getting shorter, you get ultraviolet, and then X-rays, and then gamma rays, huh? Pretty amazing. And look, it's all connected. From radio waves to gamma rays to visible light in between, it's all frequencies of electromagnetic radiation. How is it staying up? So everything outside of the visible spectrum is invisible, right? Wrong! Ha-ha! Bam! Huh?
That is an X-ray, a picture we can take using this part of the spectrum.
We can use special cameras to see outside of the visible spectrum. Huh? Huh? Right? Yeah. Okay, you got it. Huh? And look at these. These are night vision goggles. They help you see in the dark. They use part of the spectrum called infrared.
For those of you keeping score, that's this part of the spectrum right here.
Pretty neat, right? I would sell you these, but they're already spoken for. Oh, and here he comes now.
Hey, Sal.
Hey, how you doing?
You got those goggles I ordered?
Yeah, go ahead, help yourself.
Thanks for putting them aside. Can I put them on my tab?
Yeah, no problem.
All right, thanks, Sal.
Okay, see you later. Nice kid. He's always in a rush, though.
Bill? Is that you?
Yeah.
Do you need the flashlight?
I don't. Turn it off. I can totally make my way over to you. Oh.
I can hear you.
Yeah, I'm right here.
Oh.
Right here.
Hi.
Because I have night vision goggles. Ooh, check it out.
Oh, cool.
Pretty cool, right?
That's awesome.
So here's the spectrum again, and here's visible light. My night vision goggles use infrared, this part of the spectrum here with wavelengths just a little bit longer than the red we can see.
Outside of the visible light spectrum.
All right, I would say that's allowed.
No visible light, and I will see the next ball. Have you got it set up?
I set it up while you were out.
Okay, good. I'm gonna sit in the chair and see if I can see it.
Okay.
Here we go. Oh, wow, I can totally see everything.
Can you tell me what the ball says?
It says you win.
Nicely done.
So let's recap. This challenge is the same as the last challenge. The light from the ball was magnified by the lens, sent around a corner by reflecting it off a mirror, and flipped back around by using another mirror. But this time, it's dark. So, using infrared light, thanks to my night vision goggles, I was able to see the ball and win the game.
The light manipulation challenge is done. Science Max experiments at large. Time to turn the lights back on.
Yep, absolutely.
Huh.
What did you do back there?
I guess we blew a fuse or something.
Uh-oh.
These are night vision goggles. They use some of they use some things that I cannot pronounce.
Have this container of water.
Whoa!
And I make it stream. But instead of going straight back, they're going.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode of Science Max is all about elastic energy. We use it to build a catapult and a paddle wheel boat, and then we max them out. We even learned some history. Elastic energy. Today on Science Max, experiments at large.
Welcome to Science Max Experiments at Large. I'm Phil McCordick, and today we're going to be building one of the most devastating, one of the most powerful machines known to medieval man, using a plastic spoon, among other things. We're going to be building a catapult. Catapults were used throughout history for all kinds of reasons to throw all kinds of things, but mostly big stone blocks at castle walls in order to knock them down. Here's what you need in order to build your own catapult. You need elastics, pencils, unsharpened is fine, plastic spoons, like I said, and popsicle sticks. Popsicle sticks. Popsicle sticks. I'm gonna go wash my hand. So, here's the science behind what we're doing today. It's all about elastic force. Elasticity is a property of solid materials, like this elastic, and how much they tend to return to their original shape when deformed, like when I pull on it. Elastics are called elastics because they're great at doing just that. You can pull on it and pull on it and pull on it, and it'll, always return to its original shape. So we are using the power of elastic force today. Ow.
Now it's time for a Science Max quiz. Elasticity is the ability for a material to return to its original shape when deformed, like this or this. Which of these materials have elasticity? A rubber band, a pencil, or a rock? Haha! This is a trick question. The answer is all three. Most solid materials have elasticity. Nearly everything will deform a little and still be able to return to its original shape. It all depends on how much. This is a steel bar. This is an elastic band. And this is an ice cream sundae. We're not talking about ice cream sundaes now, though, so get that out of here. Good. Now, a steel bar and an elastic band both have elasticity. A steel bar can be stretched to 1% of its length and still spring back. A rubber band can be stretched 300% or more. The difference between the two is why we make balls out of rubber and buildings out of steel, because the other way around wouldn't be good for balls or buildings. This this has been a Science Max quiz.
All right, let's build our catapult. The first step, take 4 pencils and stick your popsicle stick in between so you have 2 on the top and 2 on the bottom. And then use your elastic to go around and around and around. That's why I like building things with elastics, because it makes it very fast to tie things together, because once you go around and you have it nice and tight, you just pop it over the end and voila, it stays together. And that is how you start making your frame. Put more pencils on that side and another popsicle stick on the other end, held on at the corners with more elastics. Then take even more elastics and put them right around the middle until you get this. I've added a few more elastics around the middle here, and that is where we're gonna get all of our elastic force. I think I have 6. The more you use, the better it's going to work. Take your popsicle stick, stick it in between the elastics, and then start spinning it around. Here's the reason I use pencils and popsicle sticks, is because the pencils are a little bit longer, which allows you to twist the popsicle stick around in the middle and build up the elastic force. Now, because I'm twisting, the elastic force we're using here is called torsion, or twisting force. When you feel you have enough torsion, pull your popsicle stick down a little bit so it won't unwind on you, and you'll see that you have all kinds of elastic energy. Then, take your spoon and stick it on the popsicle stick, and you can also break off the popsicle stick if you want to make sure it's the right length. And it works like that. To make the frame, you just need more pencils and elastics. The trick is to make a triangle with 2 pencils attached to your frame. They should stick up right where your catapult arm would be fully upright. Then, take a final pencil and put it across the top. Don't forget to pull the arm back before you put the pencil across, otherwise it'll end up on the wrong side. Now, this is very complicated, and I went pretty fast, so if you want the step-by-step instructions on exactly how to build this, go to our website. And there you go, a catapult of your very own that you can use to knock down very small castle walls. I've also built a larger catapult using all of the same principles. Pretty good, huh? It's got a longer arm, which means I can throw marshmallows even further. Whoa. Or I can throw larger marshmallows, or I can throw very large marshmallows. Whoa. Now, I know what you're thinking. You're thinking, Phil, is that the largest catapult you're gonna make? Well, of course not. This is Science Max, experiments at large. I'm headed to the Center for Skills Development and Training, and we're gonna max out the catapult so that it's big enough to throw one of these. Hey, Zach.
Hey, Phil.
How you doing?
All right.
This is Zach. He's a mechanical engineer, and you build machines for a living, right?
That's right.
Great, because I need help building a catapult.
Okay, but what's with the pumpkin?
Well, the pumpkin is what I want to throw out of the catapult. See, I figure we just take the small design and we just make it so that we can throw one of these. What do you think?
You're gonna need a really big catapult.
Yeah, and I'm also gonna need some really big elastics. Where do you get those?
Well, in medieval times, they used rope to make large catapults.
Oh, okay, well, rope is a lot easier to get, and that would be fine. And I want to make this arm as long as this piece of wood here.
This is gonna be a huge catapult.
It's a huge catapult. I guess we should build it outside, though, huh?
Let's do it.
Okay, it's over that way.
Okay.
I'll follow you.
Sure, do you want a hand with that?
No, I'm fine. You go ahead, and
Okay.
I'll just, maybe if you hold the door open for me, I could just hold, no, you know what, you go and I'll meet you.
You sure you good?
Our full-size catapult is going to look a lot like the popsicle stick version. We start with a 4-sided frame and add some legs on the bottom. Our spoon is going to be replaced by a long throwing arm with a basket on the end. Then we need a really strong cross brace at the top to stop the arm. Just like in the small version, using a triangle shape is the best because triangles are very strong. Finally, we need something to wind around and around, which is going to give us our elastic force. Instead of elastics, we're going to be using rope for our catapult because rope has just the right amount of elasticity. But unlike medieval times, we're going to be catapulting pumpkins. Once Zach and I got it all put together, it looked like this.
Okay, we have built a catapult. Check it out. It's pretty solid, and I think it's pretty amazing. And just like in the small catapult, we have our elastic force. But this time we're using rope, right, Zach?
Yes.
Okay, and rope will work as well as the elastic did in the small one?
Yeah.
All right, great. So what do? It's really loose now.
We need to wind this up so that we put some tension into it.
Go!
The reason a catapult works is because the rope is twisted. The elasticity in the rope wants to unwind, which gives the catapult its power. Just like the small catapult, the more you wind it, the better it works.
Good. Usually in medieval days, they had whole teams of people doing this job. But it's just me and Zach now. How you doing, Zach?
All right.
Okay. And then we clamp it on here. So the thing doesn't unwind, right?
Yeah.
Good. All right. Now we have our pumpkin, and we're gonna fire our pumpkin in our castle wall, which is made out of cardboard boxes over there. Pumpkin. All right, here we go. Pulling the arm back. Oh, that elastic force is pretty strong. Okay. How do you think that pumpkin's a good size?
It's pretty big.
You think?
Oh, a little too big.
It's too big for our basket.
Yeah.
Smaller pumpkin! Smaller pumpkin! I'll hold this. No rush, Zach. No rush. Okay, rush, Zach. Can't hold.
Oh, yeah.
Can't hold arm. Okay, ready? 1, 2, 3! It didn't work that well.
No, not quite that well.
Yeah, so
Let's see.
it went, and it flew, and it landed here, which is a little farther away from the wall than I'd like it to be. 1/3 of the way to the wall! I don't know if that's enough. What do we do to make it better?
Well, the way we're throwing it right now, we just have the pumpkin in at the end of the arm. But
Yeah.
if we make some kind of a sling so that we fling it as we're bringing it up.
We make a sling?
Yes.
All right, I don't know how to make a sling, but you know how?
Sure.
All right, we'll make it, and then you can explain how it works.
Yeah.
All right, good. Let's put the pumpkin over here. We'll recycle it later.
Max Historica.
Good morrow to you. I am Lord Fillington III, and welcome to my medieval castle. Throughout history, lords and kings have built castles and walls to keep people out. I built my castle to protect my prize collection of snow globes. I have so very many, and they're all mine. Ha ha! Oh, hello! You down there! You can't come in. This is my castle.
And throughout history, there have been people who've been wanting to get into those castles because Lord Fillington has been hogging all the snow globes, and I'd like to look at them. But the hard part is figuring out how to get into the castle, because I can't just come up to the wall and start hammering on it. Huh?
Taste the wrath of my water balloon!
Because if I get too close to the castle, he can get me.
Ha 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 ha! Fortunately, there's this thing called a catapult.
Oh, fiddlesticks. They have a catapult.
What you do is you put something heavy in the end here, and the catapult fires it at the walls of the castle, knocks them down, all from far enough away that the people in the castle can't get to you. Ah! Oh, I surrender! Don't knock my walls down! It'll take me all week to fix them. Oh. All right, you can have a snow globe. Oh. And that's how catapults were used in history. Oh, so beautiful.
Back to our maxed out catapult. Our first design threw a pumpkin just like it was supposed to, except it only threw it 1/3 of the way to the wall. Now Zach and I are planning to outfit the catapult with a sling. The sling attaches to the end of the throwing arm and gives the pumpkin a lot more distance to travel. because the pumpkin is traveling a longer distance in the same amount of time, it will be going faster, which will hopefully get it to the wall, or at least a lot farther than before.
So we built this sling. How does this work, Zach?
Well, we've got one end tied here.
Yeah.
And then we put the pumpkin in here.
Wait. Okay, pulling arm down. Pulling arm down. Okay, yeah, now what?
Now we put the pumpkin in here.
Put the pumpkin in there.
Yeah. And then we loop this over the back of the, over that. As the throwing arm goes up, this will slide off the back of the throwing arm and it will release the pumpkin.
All right, you're the expert. I believe you. Let's try it out. 3, 2, 1. Whoa! Okay, that works really well. You know what the problem is, though? We still don't have enough oomph.
Yeah, it needs more power.
So what do? I don't know if we can crank that rope anymore.
I think we're at the limit of our rope power, but if we added some more elastic.
I thought we weren't going to use elastic.
Well, we used elastics in our small demo model, so what if we use some more?
We have elastics? I don't know
yeah,
if we
brought
have
some in here just in case.
What's this?
It's surgical tubing.
It's like a giant elastic. Well, I guess this is elastic force, so do we twist it around at the bottom there?
Well, we just wrap it around the throwing arm like this.
Oh, I see. So we tie it here.
Yeah, we just need a lot more, and then
we pull this, and it would be. Oh, yeah, that would make a lot more. So we just need a lot more of this elastic. What is this again?
Surgical tubing.
Surgical tubing. It's like a giant elastic. Fantastic. All right.
Goggles on.
Goggles on. Yes. Yes.
Here's another fun way you can play with elastic force. Take a milk carton. I prefer Science Max milk because it's the creamiest. 2% cream, 100% science. Wrap some elastic bands around it with some popsicle sticks on the bottom, sort of like feet. Then take some clamshell packaging, which wraps just about anything you buy nowadays, and cut out a square or a rectangle. Then wrap some tape around that square with an elastic in it, and put the elastic on the feet of your milk carton. Then wind it around and make sure you go backwards so your paddle wheel boat will go forwards when you put it in the water. And there you go, a paddle wheel boat. Now it is time to max it up. Ahoy, the SS maxed out elastic force paddle wheel boat mattress. I need a better name. But I've made a giant paddle wheel boat that will work on elastic force because I've got surgical tubing as my elastics, and that's an air mattress. And then I use some lumber to hold it all together. And of course I need a paddle wheel, and what better thing to use in a pool than a flutterboard? Okay, here we go. So normally you're not allowed to wear your clothes and your shoes in the pool, but I got special permission because of science. Besides, I'm not worried at all, so I didn't wear my swimming outfit because I figure I can totally do this entire experiment without even getting wet. That is how confident I am. All right, now the tricky part, we'll be getting onto the mattress. Okay, here we go. Ha-ha! Whoa. Ha-ha! The SS Science! Hey, SS Science, that's a great name for this. Look, it works great, and I managed to stay totally dry. Huh? Well, almost. Whoa, oh, oh. Haha, you thought I was gonna fall in the pool, but I didn't. Uh-oh. My flutterboard has stopped moving, and I'm in the middle of the pool. Almost. Yeah. Didn't think this through. No. 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 No, that's not going to work. Maybe I'll wait. Our maxed out catapult was working well with the sling we attached to it, but it still didn't make it all the way to the wall. Zach's idea is to attach a bunch of surgical tubing to the cross piece of the catapult. Surgical tubing is pretty much big elastics, so we'll have two places we're getting elastic force from, the rope and the surgical tubing. hopefully this design is enough to help our catapult fling a pumpkin far enough to hit the castle wall.
All right, here we go. You hold that. I get this. We got our system down now. Okay. This goes up to there. Okay. Okay. 3, 2, 1. Nope. One, 2, 3. Oh! It went too far. It went too far. That's so good. Oh man. Okay, so all we gotta do is move the catapult back. So you get that side, I'll get this side, and we'll move the catapult. See, now our catapult is too good. We gotta back it away from the castle. All right, let's go again. Aha, pumpkin.
Pumpkin.
Pulling arm back.
Pulling arm back. Grunting.
Loading. Pumpkin. Hooking rope on arm.
Hooking rope on arm. More grunting.
More grunting. Pulling back strongly. 1, 2, 3. Oh. Oh. Oh, wow. Woo.
We're inside the castle.
We're still inside the castle. Oh, man. It's an excellent shot, though. So what do we do? Move the catapult back?
Yeah.
Move the catapult back. What about
here?
Here. Here we go again. Pumpkin.
Pumpkin.
Loading arm.
Loading arm.
All right, you ready? You think it's gonna work? We've done every modification we can possibly do. So you think it's gonna work this time?
We did it. It's gonna work.
Okay, here we go. I'm excited. All right, ready?
Ready.
1, 2, 3. Whoa! Yeah! Woohoo! High fives! Well, there you have it. Awesome job. Now we need to throw fingers to see who gets to rebuild the castle. Okay? 1, 2, 3. Oh, thanks very much for joining us. Let's just take a break. I'll rebuild the castle. You see, this is exactly how catapults used to work. They'd hit the same part of the wall over and over until they made a big hole, and that would weaken the wall. Fortunately for me, it's really easy to fix. Just put this right in here. Oh, man. The pool will be closing in 5 minutes.
No, I'll do it. No, why do you want to?
Taste the wrath of my water balloon!
I don't believe it really sells it if he doesn't smash the water balloon. Does he? Good moral to you! I got my feather in my face.
Oh, you gotta be kidding me.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today, I'm maxing out the power of water. Water is very heavy. Pressurizing water to make a water-powered car, water pressure pumpkin carving, water flying, and more. All on this episode of Science Max, experiments at large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're gonna be looking at water. But water is very heavy, but that's okay because we need it to be heavy for this experiment to work. I don't know if I need that much of it though. Maybe I can get, here we go. Yeah, that's probably all I need.
Today, we're going to be building a water-powered car. You'll need a base for your car, like this styrofoam, water bottles, shish kebab skewers, straws, scissors, elastics, paper plates, tape, a square of paper towel, modeling clay, vinegar, baking soda, water, and glue or a hot glue gun if you have an adult to help you, and... yeah, I know, this one is pretty involved. That's why you should go to the website for step-by-step instructions. Take your paper plates and glue 2 together to make a wheel. Then make 3 more. Wrap elastics around your base and then tape straws on the bottom.
Trim them down, maybe about that much.
Then take your shish kebab skewers and push it through a water bottle cap to make a hole. Then stick one wheel on, put the skewer through the straw, and
Do the same thing on the other 3 sides.
then take the water bottle cap and get an adult to help you make a perfect hole in it so that it fits your straw. Then use some modeling clay and hot glue to seal the straw and the cap so it's airtight. Attach the water bottle to the base of your car, then fill it with some water and vinegar. Next, you'll want to wrap up a spoonful of baking soda in the square of paper towel so you can make a little package. Finally, stick something underneath the underside of the bottle to raise the end up off the base.
Bring your cap and then go outside. Here we are outside. Yeah, I know, we're not really outside, but I have a science lab and you probably don't, so I highly recommend you do this outside.
And don't forget your safety glasses.
Now, this is why we make a little packet of baking soda, because we want to delay this reaction as long as we can. So I like to hold it there. We'll hold it there with one finger so I can get the cap ready, because we don't want it to react until we can get the cap on, and then kink the straw to keep the pressure inside till we're ready to let it go. Then, at the last second, you want to drop that packet in and quickly cap it and kink the straw. And woohoo! Woohoo! Haha! There you go, a water-powered car. Now I know what you're thinking. You're thinking, Phil, wait a minute, that's a vinegar and baking soda-powered car. Well, kind of. The vinegar and baking soda create a gas, and that gas creates pressure in the bottle, and that pressure forces the water out of the bottle. But it's the water leaving the bottle that creates the thrust. The water going that way pushes the car that way. Newton's third law, every action has an equal and opposite reaction. So what we're gonna do is max out the water-powered car. Figure out how to get water going that way so we can go that way. But we means me and someone else. Who can help me? Oh, I know, Anthony from the Ontario Science Centre. He'd be great at this. Hopefully he's not busy. We're gonna max out the water-powered car. Ha. Anthony! Phil, sorry about that. Did I scare you?
Don't worry about it.
How you doing?
Awesome, thanks.
Great. I was wondering if I could get your help on an experiment.
Yeah, okay. Which one?
I'm building a water-powered car. It's gonna be great. It's Science Max headquarters. I'll show you.
Phil?
Anthony, I'm here.
Whoa. Phil, where are we?
Oh, this is the parking lot for Science Max headquarters. So,
Okay.
today, I want to max out the water car.
This thing is awesome.
Yeah, so what you do is you use vinegar and baking soda,
Yeah.
and you pressurize this container, and,
Okay.
and the water shoots out that way. So the car goes this way.
Newton's third law. Every action has an equal and opposite reaction.
Yeah, you know your
Okay,
stuff. This
okay.
is why you're here. This is because I could really use your help and advice on how to make this bigger.
Okay, so we're gonna need a bigger tank to pressurize. So this, what about something like this?
So we need something that can hold pressure. Do you think this would work?
I don't know if we'd wanna...
And we'd have to put like pressure fittings on the barrel, like cut a hole
Yeah.
and weld them on. I don't know if that's...
Something tells me this wouldn't work, so we
Okay,
need,
sure. I got some other stuff over there maybe that we could use.
Check this out. Yeah, I think this would work. This would work a lot better.
Well, this is my stand-up wash tub base.
Your what?
So
Yeah.
we'll reuse it. Yeah?
Okay, you know what I'm thinking
Yeah.
now, though? I know
Yeah.
this... The problem is, I think this is like an oil drum, right?
It is.
And,
It's an oil tank from a house.
and these things are not built for pressure.
You can get water tanks that you pressurize.
Like hot water heaters, yeah, you can pressurize. They're built for that stuff. You pressurize them in your basement, and then the water travels up to like
the top
your
floor.
shower
That
or
makes
something like that.
So all we need to do
is get a pressurized water tank.
Okay.
Put water in it, put pressure in it, and put it on wheels. And then we open the valve and it goes, right?
That sounds amazing.
All
yeah,
right.
let's get to it, man.
Okay,
we
I
need
got
to-
some water tanks over here in this corner of the parking lot.
Seriously?
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. When you're a professional chef like me, you spend lots of time perfecting the perfect recipes. I know my way around a kitchen, and today I'd like to show you one... That's not the fridge. Oh. Today I'd like to show you one of my favorites. Quail truffle gazpacho cakes on a plate of ice. Beautiful. And here's how to make it. Take some quail, some truffle, and some gazpacho and put it into a cake. Delicious. And here's the interesting part. How to make the plate of ice. Ooh, how did I do it? Well, I tried many different methods, and none were very successful. But now I let science do the work for me.
So here's what I do. You see, I've got my large block of ice, and I've got a fishing line over the top, and on the bottom, I've got 2 heavy weights. Now we wait.
The heavy weights put pressure on the fishing line. This pressure melts the ice where it's pressing down. As the ice melts, the fishing line moves through the block of ice and eventually cuts its way through.
There we are. My hours of waiting have almost paid off. You see, I've got a perfect line through the ice, and I stopped it just before it finished. It's the pressure of the line on the ice that makes it work. The same thing happens when you use ice skates. You see, it's a very thin line, and your body weight presses down on the ice, melts it a bit, and that allows you to glide across the ice. It also allows me to just pop this off. There you are, you see? Perfect plate of ice to put my delicacy on. Let's just try that now. There we
So I've joined Anthony and we're going to max out our water-powered car. Our small design works by creating gas, which creates pressure, which forces the water out of the bottle, creating thrust. Our new plan is to get a water tank, put it on wheels, and put water in it. Then we use an air compressor to pressurize the air inside. When we open the valve, the water is forced out this way, which causes our water car to go that way.
Okay. Ha-ha! So, water car, maxed out version.
huge.
Water tank.
And filled with lots of water and lots of air. Too. Yeah, pretty good, right?
Whoa.
It's a lot of it. So,
Did it mess up my hair?
no, you look fine. You look great.
Okay, good.
Now, the only thing left is we just gotta open this valve here, right?
Yeah. You want to do the honors?
Yeah, let's do it. Okay.
Okay, here we go. 3,
2,
1, go!
We open the valve and our pressurized tank moves forward. The air pressure in the tank forces the water out with enough force to move the tank.
Awesome! That was awesome!
That was a great run, yeah.
That's amazing.
So, pressurized water tank on wheels.
Totally worked.
Totally works.
Total success, yeah.
So, because this is Science Max, the only thing we can do now is make it bigger.
Bigger,
right?
exactly,
Okay.
yeah.
So, problem is,
I don't think we're gonna find a tank bigger than this one.
Yeah.
So
because then it would be too heavy, right?
exactly,
Much
way too
bigger.
heavy. Maybe what we can do is just get a lot more water.
Okay.
And then we find a way to pressurize the water.
Oh, so don't pressurize the whole tank, just the stream of water that's going out
As
of
it
the tank.
comes out, exactly. Something kind of like a fire hose.
A fire hose, right.
So
we take a big container of water,
right?
and I guess we would need a pump.
Yeah, like a pump would be perfect.
So then we suck the water out of the container, put it through the pump to pressurize it, shoot it out of a fire hose.
And then our car goes flying.
Goes flying.
Okay.
Yeah, let's do it.
Yeah. All right. Amazing.
When water is going fast, it has a lot of force. This is a power washer. It's made for cleaning concrete and wooden decks, but it doesn't use soap and it doesn't use heat. It only uses the power of water. Let's try it out.
The power washer creates a stream of water that is moving really fast. It has the force to clean concrete, strip the paint, or even the Science Max logo off wood. But how do I max out the power washer? What's the most ultimate use I can think of?
Power washer pumpkin carving.
The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home.
Yeah, science!
The Wizard Academy. All you have to do is demonstrate true magic, and you'll be granted entry.
Send in the next candidate. Oh, no, not Overwhelmo.
Did someone say Overwhelmo?
No, wait, no. Next. Oh, not that. Okay, good. Okay.
Behold, it is I, Overwhelmo!
Welcome back, Overwhelmo. If you can truly demonstrate magic, you may join the Wizard Academy.
A glass of water! No, wait, that is not the whole trick. Okay, hold on. Okay, and this, a waterproof playing card. I put the card on the glass and flip it upside down, and then I say the magic word. The magic word. And behold, magic! Yes?
Is that it?
Yes?
Well, it's not magic.
It is defying gravity.
Nope.
The water would fall and the card would fall to the floor.
It's not magic.
This is magic.
No, it's science.
Horse feathers.
Look, the reason the water doesn't come out is the air at the top of the glass keeps it held in by suction. More air would have to get into this glass to decrease the suction, and because the playing card is keeping a seal on the glass, the suction of the air is holding the weight of the water up.
Boulder Dash!
All right, look, let's do a little experiment then, shall we? Let's move the playing card just a little bit from the edge of the glass. You see those bubbles?
Yes.
That's bad news. Science, not magic.
Well, I will return, and then you will see your mind will be melted by the... No, that's not my music. Hold. You will rue the day when... That's not my... Hold. Overwhelmo shall return!
Our maxed out water car worked pretty well. Now it's time for something even more maxed out. We start with a giant tank on wheels, we add a pump to pressurize the water, and a fire hose to shoot it out the back. What's more, this version is big enough for me and Anthony to ride.
Water car! Amazing! Is the more super improved water car. This tank holds 1,000 liters, and right now it has 720 liters of water.
We have a pump, that's right, our water pump. So the idea is we take the water from this container out through your hose, really pressurized, going really fast that way. Our car goes really fast this way.
All we gotta do is just turn on the pump, and we're ready to go.
So we fire up the pump and the water stream comes out really strong. So strong I can barely hold on to it.
Here we go!
But even so, there's a problem.
What's going on back there? I got it! Yeah.
Nothing happened.
No, nothing really. Well, something happened. We got wet, but it didn't really.
It's too heavy.
Too heavy.
So you're on it and I'm on it. That's a lot of weight. We don't ride it. That's something.
Yeah.
Also, this is kind of going crazy.
Yeah, because if nobody's holding it, it's just gonna flap around.
So we'll have a brace here.
Yeah.
Shoots it that way, that's good.
And then we'll need, I feel like we'll need something to kind of propel it. Maybe a better propulsion system. Kind of like one of those steamboats.
So we put a big paddle wheel here.
Exactly.
And we aim it, I guess we aim it down
at the, yeah, exactly.
like that.
And then
at the paddle wheel, and then the paddle wheel spins, and that propels the car.
Exactly.
Right?
Right.
Okay.
Okay, well,
we can do that. Let's do it.
Sounds good,
We'll
yeah.
put it together. You know what? I have a paddle wheel because I had a failed hydroelectric. This is called flyboarding. Whoa! Whoa! Powerful jets of water are being shot out from this board at my feet. Whoa! The engine on the watercraft behind me creates the water pressure, which travels up the hose and through the jets. The force of the water is strong enough that I can use it to fly around. So what's the difference between this and a water car? Well, we don't have to take that much water with us because it starts in the lake and ends up in the lake. So the only water I have to carry is in the hose that goes up to the platform. Woo-hoo! Flyboarding is lots of fun, but it takes some practice to get it right. Balancing on jets of water isn't easy, but I got the hang of it. It's all due to Newton's third law. For every action, there's an equal and opposite reaction. Physics! Woohoo! Our maxed out water car didn't work so well. The main reason is that much water is heavy, 720 kilograms.
Yeah.
So Anthony and I have a plan. Rather than rely on the force of the water going straight out the hose, we're gonna put a water wheel on the back of the water car. A water wheel works by catching water in the segments of the wheel. The weight of the water on one side of the wheel causes it to start turning. But we're gonna use the weight of the water and the pressure of the water. Hopefully, both combined will be enough force to turn the wheel, which will drive our water car forward. A little construction, and we have it ready to go. Okay, so here's the latest version of the water car, water wheel! Yeah. All right.
Yeah, there we go.
We try it out, but there's a problem. The trick with the water car is the water itself weighs a lot. Every liter is 1 kilogram, so our 720 liters we start with is way too heavy to get the car moving in the beginning. But as the water gets pumped out, there's a sweet spot where the weight is low enough the water car might move. But then there's only a little water left, so it's a balancing act. We fill it again and see if we can come up with a plan. Okay, new and improved version, only half full. So the idea this time is because we're starting with it only half full, right?
Yeah.
Then it'll begin to go a little easier because it won't have as much weight as it had the last time we did it.
And Phil,
Yeah?
I can't even move this thing.
What?
I think there's too much fuel. There's too much. Yeah, there's no way we can move this. There's no way this is gonna be able to move
Even
on its own.
half full, you
Even
can't
half full,
move
I
it.
think we need less fuel than we gotta get down to like maybe like a quarter or something like that.
The thing is, we ran it from the full tank last time, and it never
So
moved at all.
What if we gave it like a push to kind of help it get over that little bump of energy?
Ah, so give it the first push when it's still got a bunch of water in it. We give it a bit of a push, and then maybe it'll go on its own.
Exactly.
Okay.
Wanna
Yeah.
get it
Absolutely. Let's do it. We start the pump and wait for the amount of water to get to just the right spot. Then we give it a push while it's still kind of heavy to start it moving. Sure enough, that push makes all the difference.
Yeah, it's working!
The water car is light enough to roll, has some momentum to keep it going, and the force of the water coming out the pump is enough to keep it moving forward on its own.
Still going!
All right!
Amazing! Yeah! Look at it, man! This thing worked like like a beauty.
It worked out. It went all the way.
Yeah.
Way to go. The water car, finally a success. It was the push.
It was the push. That's all we needed to get it going.
A bit of a push to get it going and a lot less water. And there you go. It totally works. All right, you want to do it again?
Absolutely.
All right, here we go.
Okay.
See you next time on Science Max Experiments at Large.
So much easier to push it without any water inside it.
Ah! Let it go and...
There we go. Oh, careful.
I can't really see with my goggles.
Behold the power of physics. Yeah.
The door's full. This is called foot. Whoa! All we have to do is wait.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about liquids. What makes something float or not float?
Oh no! My loonies!
Liquid density and super absorbent gel.
Who wants to do an experiment with diapers?
Liquids. Today on Science Max, Experiments at Large.
Hey, welcome to Science Max Experiments at Large. I'm Phil McCordick, and hold on a second, I'm just gonna change. Okay, that's better. Now, where were we? All right, let's go make a boat. So you know that some things float and some things sink, like rocks, or wood, or full water bottles and empty water bottles, or carrots, foam, waffles, screwdriver, playing cards, plasticine, tinfoil, potato, my watch. Wait, that wasn't supposed to go in there. So how do you make a boat? You make it out of something that floats, right? Well, most boats are actually made out of metal. Tinfoil is metal and, well, it sinks. But if you fold tinfoil into a boat shape, it floats. And boats don't only float themselves, but they can hold people and cargo. In fact, there's container ships crossing the ocean at this very moment that are holding thousands of tons of cargo, and they're all made of metal, which doesn't float, it sinks. So how do boats do it? Are they magic? No, of course not. Boats are science. And here, you can be science maximites. Get some tinfoil and cut it into the same size pieces and fold a couple different shapes of boats and see which one can hold the most weight before sinking. And now it's time to max it out.
But before we do, here's how you can fold your own tinfoil boat in less than 15 seconds. First, take a square piece of tinfoil, then fold it in half. Fold one corner down and the other corner down. Then open it up and ta-da, you're done. If you want instructions on how to fold a more complicated boat, go to our website.
I have a feeling I'm gonna need a few extra lab coats for this experiment. Like I was saying, let's max out the tinfoil boat and find out a little bit more about why boats float. Okay, well, I'm here at an indoor pool, which is not, I wasn't expecting to be in the pool just yet, but this is where we're gonna build our giant tinfoil boat, so why not? Huznia.
Phil, you're wet.
I thought I was gonna come in over there, but I came in on the water sled. I think I had the coordinates wrong. Anyway, this is Huznia, and she's from Let's Talk Science, which is all about science education, right?
Yes.
Just like us. So you're gonna help me max out the tinfoil boat.
I think I dropped it in the water. Hold on. Whoa! Here. Where? There it is.
The tinfoil boat. The tinfoil boat!
Bill, this is a boat?
Well, it looked a lot better before I came down the water slide, but that's the idea, and then we make it bigger. What do you think?
I don't think it's gonna work, Phil.
Oh, well, why not?
Tinfoil is very thin, and it might not hold the shape of the boat.
Well, I still think we should use tinfoil, though.
Why?
Well, because the small experiment was tinfoil, and I bought all of this tinfoil.
Then let's do it.
Tinfoil? Okay, high five. I will, I'll take the tinfoil, and you take that, and I'm gonna have to dry off at some point.
Welcome to Shipbuilding for Pirates. I'm Swubby, and I've built some of the finest pirate ships for some of the finest pirates this side of the Caribbean. And I can teach you to do the same. But first, you need to know your basics. Mass and volume. Let's start with volume! But not that kind of volume. Which of these two chests do you think has more volume? Right, this one here. Which of these two balloons do you think has more volume? Right, this one here. Volume is how much space something takes up. Which of these two chests has more volume? That's right, they're the same. But which of these two chests has more mass? Which is heavier? Hard to tell, isn't it? But what if I told you that this one was empty and this one was full of treasure? Oh, loonies. Now, which one has more mass? That's right, this one. These two chests have the same volume, but this one has more mass. This chest has more volume than that one, but this one... My loonies! That chest does not have as much mass. Volume is how much space something takes up, and mass is how heavy something is. And when you look at them both together, you're looking at density. Join us next time on Shipbuilding for Pirates, and then we'll look at how volume, mass, and density work together to make something float. Oh, my precious, precious loonies. Are you all right, my pretties? They can't talk, so I'm not sure what they're saying.
So, Husni and I get to work constructing a large tinfoil boat. Our first design is just sort of a square, folded together out of a very large sheet of tinfoil. Simple, but can I ride in it?
There we go. A giant tinfoil boat, just my size. Woo-hoo-hoo-hoo.
I don't know if it's gonna work. It's too thin.
You think it's too thin?
I feel like yes.
What should we do?
Do you want to test it?
Let's test it. Okay, good idea. So here's the most important question. Do you want to test it or should I test it?
No, you test it.
All right, here we go. Putting it in. First test, does it float on its own? Yeah! Floats on its own, no problem. If I just get in very carefully, then it will work fine. See, if I'm careful about how I get in, no, it's fine. See, if I just get in like that.
Oh my! Bill, are you okay?
Wait a minute. It's sort of. No, that's just air. You know what went wrong? It wasn't boat shaped. I think if we make it look more like a canoe, because canoes float, if we make it look like a canoe, it'll work great.
No, Phil. We need some support. If we add a couple of structures in between, then we add support to it.
I'll tell you what. Let's make a boat like I want to make and a boat like you want to make, and we'll see whose is the best.
That's a good idea. Okay, let's do that.
All right, let's do it.
Welcome back to Shipbuilding for Pirates. I'm Swubby, and now we know what volume means, what mass means, and that together it can tell you something's density. Now let's find out why things float. Let's say we're out to sea and my treasure chest gets swept overboard. Oh no! But it's all right. It floats because it pushes enough water out of the way, displaces it to carry its mass. But what if my treasure chest had more treasure in it? Well, we're giving it more mass
but not more volume. Too much mass and not enough volume, and it'll sink. Oh no, my loonies! You need more volume if you want to float more mass. And that is why things float. I'm Swabby, and thanks for joining me on Shipbuilding for Pirates.
So, the first version of the tinfoil boat didn't work out too well.
Like that.
But my idea is to build a tinfoil boat more like a canoe to see if a different shape makes any difference.
Tinfoil canoe!
Very Canadian.
Very Canadian. The canoe part, anyway. I don't know about the tinfoil part. So, Husni and I had a bit of a disagreement of why the last boat didn't work. I thought it was because it wasn't shaped enough like a boat. So this one looks like a canoe.
What I thought is that it requires some structure.
Structure so that it wouldn't fold together.
That's right.
And we'll see how it goes.
All right.
All right, here we go. Did it work?
Nope.
Okay, your idea next. Did you know it's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool? That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and half a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful. And you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out. Ta-da! The longest length of liquid layers. 12 liquids all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really want to mix it up, but it took me a long time to make this, so I'm not going to. Our first 2 attempts at a tinfoil boat haven't gone so well. Husnia's idea is to make a tinfoil boat and add some more structure, because the tinfoil just wants to collapse when I get in it. So we start with a large piece of cardboard on the bottom, then we wrap the tinfoil around it and shape it into a boat. After that, we add some supports across the top to stop it from folding in when we add my weight to it. This boat feels a lot stronger than the one I was just in.
I told you.
So how does all of this work?
So we got some support using broomsticks and then some cardboard paper. And then underneath we have cardboard.
And so how will all of this help the boat not sink with me in it?
Right. The broomsticks will prevent it from folding this way and you won't sink.
Good.
The cardboard will prevent it from folding this way, and you won't sink again.
Not sinking is my favorite thing to do in the tinfoil boat. All right, so let's try it.
Let's do
now,
it.
Are you gonna get in this one?
I'll tell you what, Phil. If you get in and you don't sink, I'll go after you.
Deal.
All right.
All right, here we go.
It's sort of working. Oh no, water's coming in. It's sort of working.
It's almost working.
Uh-oh.
Wow.
No, go. No. No.
Hold on.
1, 2, 3, go.
Another thing I learned is that a very light tinfoil boat can be very heavy when it's full of water.
I don't know if fixing it is in the cards. I think we're gonna have to build another boat.
So what do you think we should do?
Let's add more structure.
More structure?
Oh, yeah.
What if we add like a metal rod around the outside and maybe some more metal rods and ribs? And we wrap it all in tinfoil, and you think it'll work?
Let's give it a try.
Let's give it a try.
Don't worry about it. I got this.
No, I'll get it. I'll get it.
Sure?
Who wants to do an experiment with diapers? Oh! No, I'm serious. You may have a little brother or sister at home, which means you probably know where you can find some diapers. But there are 2 things you need to remember. First, ask an adult if you can use the diapers for your experiment. And 2, only use unused diapers. Okay? Okay. So, you take the diaper, and if you cut it, be very careful, maybe get an adult to help you, over some black construction paper, like I have here, and you shake the diaper over the construction paper, you'll see that there's a little powder that comes out. And this is the secret ingredient. This is super absorbent gel. What it does is it soaks up all the liquid, and diapers are full of them. And you carefully pour it into a plastic cup, like that. Now you can see I have already done it with a number of diapers. It's important to use a plastic cup because it's a little messy, although it's non-toxic, it's totally safe, but it's still easier to clean up by just throwing the cup away. Now, add some water, and what happens is this super absorbent gel absorbs the water and turns very quickly into a paste. Look at that. Now, let's max it out. 5 kilograms of super absorbent gel, 500 liters of water. Now, it is time to do science! And I have my own stir stick. Yep, definitely coming along. I'm not exactly sure if we're getting anything on this camera, but I want to make sure it's recording. Yep, it's recording. There we go. It is definitely turning solid. Well, there you go. The giant super absorbent gel experiment. Corey, Trevor, I need some help getting out. How many outfits have I been through in this episode? How many outfits have I been through in this episode? Anybody have a towel? There you go. Thanks, buddy. That's great.
Husnia's idea of adding structure to the tinfoil boat was definitely right. We just needed to go further. So we did it again. This time, we made a much larger boat. We started with a sheet of cardboard, then wrapped the tinfoil around and added some metal supports taped to the cardboard across the boat this way to make ribs, as well as some other supporting pieces in the front and the back. then another metal rod all the way around the top, and finally, supports across the middle. All right, feel how strong it is. I'm really excited about this version of the tinfoil boat. What we did is we used thwarts, big hard pieces of wood that we did last time, but this time we have ribs.
Ribs, right, which are made of a cardboard, a metal rod attached to it,
and shaped, and we did a whole bunch of them that go the whole length of the boat. And then we used all of this bendable metal, and we have one that runs all the way around the gunnels, and a whole bunch that run down the inside, and we even used bike fenders at the front and the back of the boat to give it super rigidity so that it hopefully won't go like all the other boats have done so far. Are you ready, Husnia?
let's do this.
1, 2, 3, lift. All right, moving it over. It floats, but that doesn't tell us anything because they've all floated at this point. It's only when I get into it. Okay, here we go. All right. Hey! Hey, it works! All right.
Oh, it's working.
Ha 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 ha! Look at that! It works perfectly. The tinfoil boat experiment has been done. Science Max, experiments at large. What do you think, Husnia?
The only reason I got into this boat because I knew it's gonna work.
Really?
Oh, yeah.
So you knew you would never get wet? See, I don't think that's fair. I think it's time that you got wet. I think we should go. I think you and I should just get wet right now. Just need
someone help.
You're still dry, aren't you?
Okay.
That is so unfair. Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Science! I don't know what you're saying. I don't speak treasure chest.
The one thing I'm really trying not to think about is that this is the stuff that's in diapers.
Let me talk to your brother. Whoa, 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 whoa. Don't talk with your mouth full.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about vibration and frequency. Frequency and vibration. What's the difference? We build a maxed out vibrobot, spin a giant disc, suspend water, and play with lasers. All on this episode of Science Max Experiments at Large. Greetings, Science Maximites, and welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max Experiments at Large, we're going to be looking at vibration. Vibration is when things go back and forth, and back and forth. All kinds of things vibrate, like pendulums. Pendulums. Wait, and pendulum. Pendulums are designed to swing back and forth. Stop that. Also, metronomes. Metronomes are used by people when they're practicing music to keep accurate time. Yeah. Okay, putting it back. And okay. We're gonna be building. Whoa, okay. We're gonna be building
this little guy. This is a vibrobot, and he vibrates and he skitters around on the paper. And if we take the caps off the markers, he makes interesting patterns on the paper. Okay, so let's get started. Let's build a vibrobot. Okay. Oh yeah, you know what? Maybe it's time to take off the ski boots, huh? Whew. There we go, that's better. So today, like I said, we're gonna be making a vibrobot. And here are all the materials you need to make your own. Plastic cup, 3 markers, an electric motor, just make sure you ask an adult first, a battery, a plastic drink bottle cap, a toothpick, scissors, this kind of tape is called electrical tape, science tape, which is the same as invisible tape, but of course I use this tape only for science, and some modeling clay. And these are 2 bendy straws that I've taped googly eyes to. These are not necessary, I just like them for decoration. Now remember, if I'm going too fast here, which I probably will be, you can get all of the steps on how to make your very own vibrobot on our website. Okay, so here's how you get started. First, you're gonna make the feet for your vibrobot. So I attach some science tape to the markers, and then I put the marker on the bottom of the cup. And then I do that again to the next marker, and then the third, balance it like that. There. Next thing you wanna do is take your plastic drink bottle cap and make a hole with a toothpick. You wanna make it off to the side, right about there. Just like that. That's so when it turns, it will be off center. That's what's gonna give us our vibration. So once you've made that hole, take some modeling clay and stick it in the cap to give it some weight. When you've done that, stick it onto the shaft of your motor like this. See how it's off center there? Now we just need to attach it to the vibrobot. I just put it right here on the top, and I like to attach the battery to the back of the cup. And now finally, we're going to attach the eyes. We take some science tape and we put the straws